Welcome back, everybody. Today, we're going to keep playing around with our motto of calculus, putting that to work, and computing definite integrals. Last time, we saw how summation notation could help us out. We saw how summation works with constants, how summation works when we have constant multiples. Right? We saw that we could just, with constants, that if you add up a constant n times, you get n times that constant. We saw with constant multiples that, I'm still in rectangle mode, that we could just pull those out outside the summation, and this was just pulling out a common factor. And we saw also that our summation, if we are summing over either a sum or difference of things, that summation distributes nicely to each of those pieces. We put those to work with a fun little computation. At least I thought it was fun. Computed this here, putting our formulas to work. And then we went to an integral. And once again, computed the integral from 0 to 2 of x cubed, right, as a limit of Riemann sums. At this time, we used summation notation to represent that Riemann sum. And we were able to figure out the different pieces we needed and work it through. So today, the plan is to just work one more of these to get more comfortable working with this notation and how it goes. And then we'll do a little debrief afterwards and make a few observations. So here's what we're working on today. Let's compute the integral from 0 to 1 of the function 4 minus 2x dx using a limit of Riemann sums with right endpoints for evaluation points, as we've been doing. And here again, let's use summation notation in our work. And here is a formula that will prove to be helpful somewhere in the middle of our computations. The sum from I equals 1 to n of I equals n times n plus 1 over 2. It's taking a summation, writing it in a nice closed form way. All right. Let me give us just a little nudge out the door with this one. Right? To start, how we've defined definite integrals as a limit of Riemann sums is as a limit as n goes to infinity of our n rectangle Riemann sum. Right? And with summation notation, we can write this n rectangle Riemann sum like this, the sum from I equals 1 to n, right, of our areas of our rectangles. They each have a width, delta x, and the height comes from the function evaluated at some evaluation point. Right? So really, at this point, if we're wanting to start move ahead, we got two things we need to find. We need to figure out our width, delta x, and we need to figure out, right, the pattern in our evaluation points and figure out our ith evaluation point. All right, let's get a start. Pause the video, see how far you can get. Then we'll start working through, and we'll go from there. Yeah, let's work away on this. It's going to take a fair amount of work, but we can do it. Let's just start in. All right. Well, to start here, let's draw our little number line of the interval that we're looking at. All right, think about delta x. We have our formula. So with n rectangles, our width is, right, b minus a over n. So for us, boils down to 1 over n. Next, we want to figure out our evaluation points, right, which for us are our right endpoints. And well, if our first rectangle has width 1 over n, well then its right endpoint is going to be smack dab at 1 over n. Similarly, our next rectangle also has width 1 over n, so its right endpoint is going to wind up at 2 times 1 over n, or 2 over n. All right, and similarly, the third right endpoint is going to be 3 over n, the fourth would be at 4 over n, and in general, the pattern that we see is that the ith evaluation point, xi star, is going to be I over n. And so with that, we know our delta x, we know our xi star, we can plug them in. What's next is taking our I over n and actually plugging that into our function f. Right? But our function f is 4 minus 2x. All right, and so whatever we hand our function, it's going to spit us back 4 minus 2 times that thing. Well, we're handing it I over n. And so if you haven't yet worked past this point, pause the video again and see how much farther you can get, plugging I over n into our function, multiplying that whole thing by 1 over n. Once you do that, we should be able to use a little bit of algebra and our summation notation properties to break this thing apart until we have formulas for the different sums that we're looking at. All right, well, if we plug it into our function, we're going to get 4 minus 2 times I over n. Right, and all of that will be multiplied against the 1 over n. Right, big parentheses here, because the 1 over n is multiplied against our entire function's output. All right, now there's some different paths we could take. I'm going to take this 1 over n on the outside and distribute it to both these terms inside, just to deal with these parentheses here. We'll get 4 over n on the left, and we'll get, if we bring the 2 up into the numerator, we'll get 2i over n squared. All right. Now looking at what we have here, we have a sum of 4n minus something else. Right? And so, well, we know how summation works, with differences. Right? Our summation is going to distribute to both of these pieces. Right? So if we do that, then we get the following. Now let's think about what we have here. Looking at the sum on the left, right? When I equals 1, what we're adding up is 4 over n. When I equals 2, our term is 4 over n. When I equals 3, our term is 4 over n. And so what we have here is actually a constant. All right, this is not changing as I changes. And so, right, this sum of a constant, well, we know how to deal with that from our formulas, right? If we're adding up this constant n times, well, then we're going to get that n times our constant, 4 over n. Over here on the right, similarly, what's changing as I changes is only the I, right? The 2 over n squared, that doesn't change. It's always 2 over n squared, whether I is 1, 2, 3, 4, 5, etc., up through n. This 2 over n squared is a constant multiple, so we can take that and pull it out. So it looks like here I have not yet adjusted this sum on the left. That'll be coming. But over here on the right, once we pull out our constant multiple, wouldn't you know it? All right, here we have our sum of I equals 1 to n. This is exactly the sum that we were told about up above. Right? So this sum if we were to write this out as 1 plus 2 plus 3 plus 4 up through n. And we're told how we can write that in a nice closed form way. So we can swap that out here, and this sum on the left, as we mentioned, we can swap that out for n times 4 over n. All right. So at this point, we are happy with our progress because there's no more summations going on at all. We just have this nice function of n, closed form, no ever-increasing sums or anything like that. Here we can now just do some algebra and apply our strategy for computing this limit as n goes to infinity. Well, over on the left, these n's happily cancel. Over on the right, 2's will cancel, right? Everything's multiplied and divided. And let's see, one of these n's will cancel with the n up top. And so simplifying down, we are left with 4 minus n plus 1 over n. And there's different ways to see what we're going to do next. I'll just literally apply our strategy here. Take the highest power of n that I see in the numerator, pull that out of everything. All right, so it'll come out of the n, it'll come out of the 1, and similarly pull out the n from the denominator. All right, what we're left with is 4 minus, pulling out the n up top, we're left with 1 plus 1 over n. And pulling over the n in the denominator, we just have a 1 left over. All right, but now these n's out front, they cancel. And since those are gone, we know how to take the limit of everything that's left as n goes to infinity. Right? 4 is just hanging out. And this 1 over n is heading to 0. All right, so here we can actually compute the limit. All right, so we're excited. We're computing the limit. We're dropping the limit notation. Here's what this limit equals. It equals 4 minus 1. I guess that should be plus 0 to match our work up here a little bit better. 1 plus 0, which is 3. All right. So, at this point, we might be feeling a number of different things. For example, I claim we are happy because we just used our motto of calculus once again to compute an area, right? To compute a definite integral. We had our idea, we had our strategy, we put it to work, and we got a result. That's cool. All right. Something that might make us feel less happy is that, well, if you think back to our function, 4 minus 2x isn't too bad, right? It's not that complicated. And we had to go through all this work to figure out the value of our integral, all right, that net area. Well, but so speaking about area, in fact, what does the graph of our function look like? 4 minus 2x. Well, it's going to be a line, right? In fact, the y-intercept is going to be 4. It's going to have slope minus 2. And so the graph will look something like this. And if we're integrating from 0 up to 1, well, then the area we're looking at isn't too complicated either. Right? In fact, we can kind of break this up as a rectangle and a triangle. All right, this rectangle has area, right? Length times width here. 1 is the width times 2 for the height. That's 2. And this triangle is going to have area 1/2 base times height. The base is, again, 1. The height is 2. So 1/2 times 1 times 2 is 1. And so if we put these together, 1 plus 2 equals 3. Okay, don't be mad at me. Don't be mad at me, right? X cubed, the one we did yesterday, that was brand new, right? That was a new area we couldn't do using this way. But this function, 4 minus 2x, we definitely didn't need all this machinery to work through. But, maybe something, a little bright side is that this is a nice kind of geometric perspective on our work, a little check that, yes, indeed, 3 is what we should be getting. All right, but, again, this is for 4 minus 2x, and, x cubed itself, wasn't too bad. Something that might make us feel a little bit worried. So what if we crank things up? All right, what about we did like x to the 10th? Are we going to need to know like some formula for like the sum of, I to the 10th power? Right, what is that going to look like? Or what if we start toss in weirder powers like square root of x? What if we start including fractions? Or, heaven forbid, trig? Right? How would we possibly try and compute a limit of ever increasing, Riemann sums, more and more rectangles? We got like sine as our function. I don't know. It'd be wild. So, with this thought, if we're wanting to compute definite integrals, if we're wanting to compute net area, we'd really like a new technique, a new approach that allows us to get a hold of these. And we will get one next week. So stay tuned, and I'll see you then. Good work today, everybody. I'll see you next time.